Okay, so welcome to the next talk. Tamer will tell us about three PCPs.
Thanks, Yael. Wow. That's what you get when you write a paper with Ron. Okay, this is a joint work with Alon and Ron. It's about a new notion of probabilistically checkable proofs. And I start by saying that we introduce this new notion with the same motivation that is to IVCs. And it gives us a very different, conceptually different approach to how to verify incremental computation. In particular, it kind of avoids this snark on snark or barg on barg or approach, and it gives us some way to build IVC, not exactly IVC, you will see in a bit, from random oracles without the need to like put the random oracle again inside something. And anyway.
Did you make the fixture?
Yes. We don't have money for it.
Wow.
So like I said, same story behind IVC. There's like a very long computation that we want to do over generations. And every new generation will do some more computation over what was passed on by the previous generation. And we want a way to verify that what we got from past generations is actually correct. And we want to do it efficiently, of course. And in a million years, all crypto will be broken probably. So in this talk, I will focus on the information theoretic setting. So we'll always be aiming to like statistical soundness. But like I said, it will also have applications to IVC if you're good with crypto and you want to like combine it with basic cryptography. Good. So you say efficient verification with statistical soundness. We immediately think about probabilistically checkable proofs or PCPs. So what are these? So we have a statement that some X is in some language. And PCPs are this proof that a verifier can look at in very few places and then decide if X is in the language or no. And he will have to use randomness, of course. And we will require like the standard completeness and soundness. Properties will be always good with small enough constant soundness error because we can always amplify, right? The verifier can always sample more random coins and check again. And PCPs, these are very powerful tools because, like, so lots of work have ended up with this like a very nice result that we can build PCPs for NP, where the proof length is almost like the size of like the circuit or the statement that you're trying to prove. And the verifier will need to look at the proof only in a constant number of locations if you're good with the constant soundness error. Amazing. OK, so our story was about incremental computation. So let's see if we can use PCPs for incremental computations. So let's say we have a PCP for T steps. OK, so we've done already T steps of the computation, and we built a PCP for that. What I want is that if I want to do one more little step of computation, then with very little effort, proportional to the effort it took me to perform this step, I can get a new PCP for T+1 steps. And I want to say that the design ideas behind PCPs are inherently they inherently don't achieve that, and we'll see this in a bit. So we do need new like ideas and techniques and so on. So let me be more specific about what I mean by little effort. What I want is that the proof for T+1 steps, you can get it from taking the proof for T steps and adding only few bits.
Sorry, I mean, I know you'll go into tree codes, but why can't you have, exponential chain of PCPs? You create PCPs of size 2 to the I for every I, and you grow it slowly, right? So then can't you just use standard PCPs to, you have to verify logarithmically many PCPs, but I'll do PCP of the last 2 steps, 4 steps, 8 steps, all the way to infinity. And now you can have, small incremental.
When you change, you have to change everything every time, no?
No, you can build it. You can build incremental pieces and then collapse
But at
them.
one point, you will need to add a PCP like that's pretty long, right?
Yeah, but you can do similar to RAM tricks, right? Or RAM tricks. You can build.
The thing is, I want to at any point to verify the entire thing. I'm not going.
Yeah. So you'll have to check like a polylogarithmic number of PCPs, but you can do. Right, you slowly build bigger and bigger PCPs as you use the old ones.
But soundness, I would assume, would rely in particular on the largest PCP.
Yes.
And at point T, it would not have been completed yet.
No. The largest PCP, if you run for n steps, you build a PCP slowly. Every 2 to the I steps, you build a PCP of size 2 to the I, right?
Let's see what you're trying to do, and then
Sure.
maybe we'll try to.
So yeah, we can talk about it. But anyway, like this, this design idea of having exponentially growing pieces, it appears.
Yeah.
It just, I think it needs more like. But we can talk.
Is Rafi's question basically, rather than going in what the t plus 1 is to do jumps of every 2 to the I? So it's just an algorithmic, it's not fundamental different thing.
I have a question about your goal for little effort. You're talking about just the size, but to do it, do you need to read? You also read very well. Okay.
Yeah. So I am being greedy here. I don't only want that this is short, I want also to be able to generate it efficiently. Yes?
Is there a reason why you don't want to allow interaction, or?
No, I'm sticking to the PCP model, and you're thinking 3 IOPs, of course.
Nobody tried to, everybody's dead.
No wants to talk.
That's what you said in the beginning.
LWA is broken implies everyone's dead, you're saying.
No, the other way around.
I will say that one way that I'm confident that you can get this from PCPs is to add a new PCP for the entire thing at every step, but this will not be short, so it will grow linearly, but we can talk about the, okay. Any more questions? Okay. So let's be more concrete. What is incremental computation for me? So let's think about this step function f, and I start with some initial configuration. And at every step, I have like a new configuration. And I will be talking about space-bounded computation. So for me, these A's, these no, not at all. I was just like giving a. Good. So I will be looking at configurations that are bounded in size, and this is a limitation of our construction. You can think about like more general things. So I will denote this by S, and I will I will measure my complexity proportional to n. For me, this is the like large asymptotical parameter. Okay. And we can also do like non-deterministic computations. So this step function will be defined by a circuit that kinds of verify every step. Okay. So for me, like what this drawing says is that the circuit taking as input the previous configuration and the next configuration and possibly some witness would verify. Good. And I'll assume all of these are of the same size without loss of generality. And also I will assume that the first configuration is always zeros, just for simplicity. Okay, now what I'm trying to prove in a tree PCP, I'm trying to prove the following language, which we call circuit reachability. So an instance in this language is a circuit, a configuration, and a number of steps. And this will be an instance if you can reach A within within n steps of applying the non-deterministic function defined by C.
So F here is C.
Yeah. F appears only in this drawing. You can forget about it. So again, this is in circuit reachability if there exists a sequence of configuration attached to a sequence of witnesses such that all of these steps kind of validate under C. Any questions? So this is the type of statements I will be proving. So 3 PCPs are in particular PCPs for circuit reachability. So at any point in time, the PCP I will have will allow me verification of instances of circuit reachability efficiently. Notice that this is not an NP language, right? Because the witness here of size n and the instance is like of size log n.
What's the input? The circuit defines the edges.
Right, and the input at any point in time is some final configuration and the number of steps. Like I assume you know what's the time now, and the instance is like the last I want to show you that by now I arrived to this configuration.
Okay, so the initial configuration is fixed.
It's fixed, like zeros. Yeah.
But then the path is non-deterministic.
Yes.
I mean, you can have.
Yes.
So you want to prove that there exists a path
Yes.
with a certain
Exactly.
at a certain depth. N is the depth.
N is the depth, is the number of steps. So a witness is again like all configurations in between and the witnesses. Again, standard completeness and soundness. And okay, so I want also another thing, which we call like incrementality. So I want that the proof for, I'm not being very formal here, but the proof for n+1 steps can be obtained by adding a very short string to the proof for n steps, of course, if the two statements are consistent. And I don't need to work a lot to compute this new appendix to the proof.
So you're defining it only for a particular type of question, which is this
Yes.
circuit
Yes.
reachability.
Yes, and this captures bounded space computations, like it's usually the case with IBC.
But why do you need even C to take a witness?
It's just more power.
It's more power,
Yeah.
but
Interesting
even
also
if C didn't take a witness,
It's
it
still
would still
interesting.
capture.
Yeah, it will be deterministic computation. Yeah.
So, in the incrementality definition, like the pi that the input pi, like the previous pi, like what has to hold for it? So does it have to be honestly generated, or is it enough that the verifier accepts it?
No, so the incrementality is only for honest provers. Okay, so I look only at honest provers if the prover can generate the proof incrementally.
I have a question though. So you want soundness for, it seems like, for soundness pi can be arbitrary, right, of course?
Yes.
For malicious pi. So it seems like, first of all, I will have to read the last part of pi, because maybe up to here it's okay.
Sure. Yeah, it will not look like the difference, we will get to it, but you figured it out. In 3 PCPs, the verifier will have to look more towards the end.
Yeah, okay,
That's what
so
you're
it's going to be
thinking.
kind of a,
Yeah.
got it, okay, good.
Sorry, it's the same question from before. If I have a non-deterministic Turing machine with bounded space, and there's a configuration that's of size, bounded space, checking whether this configuration came from that configuration can be done deterministically, even though the machine is non-deterministic. I just check, is this a valid next configuration? Somehow, maybe it doesn't matter.
Sure.
It seems to me you give even more power.
Yeah, possibly.
But I need to be careful when you read parts of the witness in different times. It needs to be consistent,
Yeah.
right?
Okay.
For,
Yes, I agree.
that's the difference.
No, yeah,
He-
of
like-
course. This is why I think it's hard to make it verifiable. I agree with that.
So if your witness is global but bounded, you can always remember it, I guess. Here it's more powerful than global bounded witness, but weaker than global large witness, I would say.
Okay, thanks.
So, what is the witness? Is the W or the AI?
Both. For if this is your statement, your witness. So if you would define a witness as information with which you can verify, your witness is all of the intermediate configurations and the intermediate witnesses. But it's not an NP witness because it's exponentially longer than your instance.
So you keep giving a new witness for every step. It's like fresh
Witness. Fresh non-determinism.
non-determinism for every step, and you don't use the previous one.
Any more questions? Yes?
For the circuit reachability, so A is like the final configuration would it be easy to generalize it to like a type of like what Surya had, like AI to AJ, or like not necessarily starting from the start configuration, but like from
Your statement is like you can go from AI to AJ.
yeah.
I can answer it. I need to think about it. I'm not sure. Any more questions? Okay, this is like I should have clicked way before, but this is what I meant by efficiently. Okay, so what's our main theorem? Is obviously a construction of three PCPs. So what are the parameters we get? We get the query so the verifier needs to look at n to the epsilon locations if n is the time so far, okay, number of steps so far. Again, I assume s is small compared to n, so I'm always fine with paying a factor that is polynomial in s. At time n, the proof grows only polylogarithmically in n. So it doesn't really grow by much. So the size of the entire proof is like almost linear in n. And computing this addition takes, for the prover, time n to the epsilon.
Each time.
Each time, yes.
Times then.
Yes.
Prover does have to work
N to the
quite a
epsilon.
bit to excavate.
Yes. That's not ideal.
We need to work in more than n.
Yeah.
And he was very large.
Yes. Yeah. This is only the first, hopefully only the first step towards like better things.
There is hope to get this to polylog n, or there is no hope?
There is hope. I don't see how our techniques can directly take you. So new ideas, it's not just laziness. It's new ideas are needed. Okay.
It's a different type of laziness.
Yeah.
So query complexity is like the verifier's complexity?
Yes.
So both the verifier and the prover's complexity grow by this factor.
Yes. Yes.
But the size is small.
Yes. I mean, for me, this is also small, but okay. Are we good?
Poly S is small, but n to the epsilon, smallish.
Smallish. Okay. I'm fine with this. This doesn't. State-of-the-art PCPs are better, but if like this is comparable to the first PCPs, if you wanna, I think. Not sure. Yeah.
They're better, but they're not incremental. They're worse
Yes,
on
yes.
the extending.
Yeah,
That's
yeah.
bad.
Yeah.
The second bullet is proof growth or total proof size?
No, proof grows with polylog n. Like the proof, like the PCP needs to be at least linear in n, right? Like at least it needs to contain the work loop.
Additive growth.
Yes. Otherwise, it's horrible.
I'm still confused.
Yes.
Why, like in the incremental error correction codes, it also applied to probably PCPs, and they usually get polylog overhead. So I don't understand why this is more difficult, right? Where it's the same question. You
need like local testability. It's a more difficult question.
What?
You need properties like local testability.
Yeah, you build PCP for the last n steps and over 2 and over 4, blah, 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 and then you increment it you update things. So the big PCP of length n, you update only every 2 n steps.
You don't need
or
to check
whatever.
consistency between like the PCP pieces or something.
Yeah, you can build PCPs and check. I mean, I don't understand why you're not immediately going for polylog.
Here.
Yes.
We'll let's top it off. Maybe we can have a follow-up that shows all of this is like shit. Sorry for the language. Okay, so I'll mention a few related notions. Incremental PCPs, they sound the same, they're not very much alike. Incremental PCPs, the requirement is you have a PCP, and it's also for incremental computations, but the requirement there that every symbol can update itself locally in some sense.
The requirement there is what?
That you have a PCP, and then at every step, every symbol, you can update it locally. And here we're fixing whatever was written, and we're just adding more.
So if you wanted to do it globally, you would have to do each of them.
Yes. Yeah. Good. A more related notion is IVC, which I kind of already hinted on the difference. So what's IVC? I mean, we've seen what's IVC. I don't need to. It's cryptographically sound, and it really quite strong succinctness, and that's why actually you need like cryptography. We do get some sort of IBC from very like the standard way you get snars from PCP. You can get some sort of IBC from 3 PCP. So what is this sort of IBC? So imagine, so in IBC usually the prover gets a short string and he has to output the next short string. He's stateless otherwise. And here what we require is that the prover maintains large memory. Okay, so it's think about always the same prover. He has large memory, he's allowed large memory, large state, but the proofs are succinct at every step, and he can compute the next proof also efficiently. Although he has large memory, but like in the RAM model, he is efficient. And due to like recent works, this relaxation looks somehow inherent to get IBC in the random oracle model. I think the arguments behind these papers, maybe Ali knows better, is that it really rely on the succinctness of the prover's input. So, like extending the state of the prover seems like the.
What would be the consequences of the strongest? Again, just can you briefly explain what these papers say in the book?
So I think the latest one says that the first one shows impossibility for restricted constructions of IBC. The later one, I think, shows impossibility in the relativized setting. So also your language is allowed access to random oracle. Correct me if I'm wrong, but I think that's the case.
So what you're saying, like with this box, is that you could get like IBC in the model where the prover has continuously RAM access to something large, but otherwise it's IBC.
In every step he's efficient, and he sends a short string. Short in the n to the epsilon sense, not as succinct as what IBC gets. Any more questions?
Is the right view you're saying this is better than the current construction? The current construction kind of takes snark and,
this is random oracle.
In the random oracle, but then you have to switch between hash function, random oracle, real function, and you don't need to do the switch.
Yeah, better is relative also, but like I'm not sure. I'm not sure how to compare.
It's like not meaningful. It's like clearly heuristic, and here at least it's meaningful.
Yeah,
to random
It's
oracle.
heuristic squared.
Like in a million years, a random oracle will still be random, right? We're good to go. Good. Okay, so let me like we agree on what 3 PCPs are and what we get. Let me talk about like how to get them. And we follow like we're inspired by like the classic way to get PCPs, right? So PCPs draw this connection to coding theory. And why is that? Because coding theory, or like the redundant encoding of information, gives us a very simple way to prove extremely simple statements. And let's imagine that the only codes that exist are linear codes. And let's imagine that the statement that I want to prove is that there exists a string that's all zeros. I mean, that's obviously true. But what you can do, if you want to prove that something is zeros, you just encode it. And if it's non-zero at one location, its encoding will have many non-zeros, and then you can just look at few random locations and capture a non-zero, right? PCPs can be thought of as a redundant encoding of computation in a very analogous way. So that's a very high level outline. So let's say we can represent our statement as the statement that some string is all zeros. What do? We write the statement down, this string down, we encode it, so this will be our PCP. And then we have to do two things. First, we need to verify that this E tilde, the encoding, is actually a code word. And for this, we usually require local testability, which I will define more formally soon. But it says that you can efficiently tell if the thing is a code word. And then you sample a few locations, and you try to capture a non-zero. This is very oversimplified, but it will give us a good initial idea. Good. So what happens now, right? I want to kind of append to my statement. I want to do a new step of the computation, and correspondingly to add to my proof. So notice that here I inherently rely on the fact that my proof has a large Hamming distance, because that's how I could capture a non-zero. So now if I stick to this syntax, to this restriction, then notice that I cannot possibly guarantee Hamming distance, because if the first error or if the first non-zero happened just now, whatever I've written is still all zeros. I will not have Hamming distance here. So like Yael noticed before, the verifier will actually need to look at these new things, because the only non-zeros, if any, will probably appear here and only here, right? Good. So like I said, PCPs from the previous slide, you can kind of see how they might be constructed from locally testable block codes. Block codes are the standard notion of codes where you have a fixed length. Tree PCPs, we construct them from locally testable tree codes. Tree codes allow us this incremental encoding, and they don't necessarily give us Hamming distance, but they give us some other distance, meaningful distance. Okay. So let's see what tree codes are. So like I said, tree codes allow us this incremental encoding. So at every step, you get a new message symbol, and you have some, let's say, code word for what you've got so far. And to encode the message with this new symbol, all you have to do is add few symbols to the encoding. So at every time step, you get a new message symbol, you spit out few code word symbols. Okay? So you can think about an encoding function that only outputs a single code word symbol, but if you, but in particular, this defines like an encoding of a message of any length. So you can think about this is like an encoding of one step, but if you want to encode a message of length 10, you just apply it 10 times, and then it will give you the encoding of the 10 symbol message.
And why are these things called tree? Where is the tree?
I will get to that. That's
the construction, not the definition.
No, it's actually in the definition.
In the definition.
And very similarly to what we've seen, again, we cannot guarantee Hamming distance, because if the first error happened at the end, what I've written so far is fixed. I can't change it. What I can guarantee, hopefully, is that I have enough errors after I've seen the first error. This doesn't sound impossible, at least. Good. So that's what led. I forgot to mention these things were introduced by Schulman in the 90s, and what he says is that we can guarantee some different notion of distance that is quite meaningful, which he calls tree distance. And tree distance measures relative Hamming distance starting the first disagreement between two words. So what I care about is I look at two code words, and I care about the amount of disagreements they have after the first disagreement. Okay? And in tree codes, usually we're interested in achieving minimum tree distance, which is the minimum tree distance between two code words. Why trees? You can think about tree codes as labeling over infinite binary trees in this case. So let's assume our messages are always binary. So every message defines kind of a path in this infinite binary tree from the root to some node. And what tree distance says is that the labeling over any two paths is quite distant starting the point they diverge. So the labeling of over this part and over this part will have to be different for any two such parts that you look at in the tree. Yes?
Sorry. What do you mean, after the word, this is the divergent in the message, not in the code word, right? Or is it
yes,
in the code word?
But because my encoding is online, if my message was the same till time 17, my code word will always be the same until time 17, because I looked at the same thing when I was encoding.
Okay, and then, so just the last part of the message where we are different, then...
I want the code words to be really different. Even if in the messages, they differ just at time t, and then they're still agreeing, I want the code words to be entirely different from point t and on.
I could read the label from there onwards.
Onwards, yeah.
But like, how is it different than just like concatenation of the first part of the message as a code word and then a code word for the second part where there are different?
If you're suggesting to always copy like what you've seen so far, the alphabet will be very large. But I'm not sure what to suggest. Okay.
If you suggest to just chop it and encode this, encode this, encode this, it won't work because maybe here you're different, and from now on you're not different. So now you're encoding the exact same thing over and over.
So once you're different in one place, you're gonna be different.
Yes, that's the point.
Okay.
Yeah. So even if these paths like from this point still take the same steps, because they took the same step, a different step here, they should have different labels. And I guess this can be formalized, but at least morally speaking, 3 PCPs are such labelings for the tree of non-deterministic computation defined by some set. Okay? I'm not claiming any form. I think it can be formalized.
Do you
Question?
want to use a step as this huge step, or do you want to use a step as like individual instruction? Because for 3 PCPs, it's usually bit by bit, you kind of extend count and code. Here, do you want to,
so here, like I have.
So gigantic step is one step. A 0, 1 is just one huge step of computation is a 0 or 1.
So you set some bound on how gigantic your step wants to be, you want it to be, but it will like even in a million years this will be the size of your.
Verifiability is not like the prover for every instruction does something. He kind of waits, gets an next witness, and then he does something. Right? That's how you should think about it.
Yeah.
Well, it can work on small pieces, no?
Yeah, I mean, it will, it will matter in the complexities, but.
So is this like similar to those like rateless codes, like the fountain, or like the raptor codes that allow you to like keep appending on?
I'm not familiar, so I wouldn't know to give an answer. Good. So let's show what time. How much time do I have left?
A little less than half an hour.
Okay, I can see that. Okay, so let me show you how to build a tree code because I think it can be insightful and useful if we have enough time to show you the 3 PCP construction. So I will show you one of the first 3 code constructions that is very generic and simple that it was not worth a paper apparently. So you take any error correction code and I want to build a 3 code out of it. Okay, so let's think about like Reed Solomon or what your favorite block code. So I will tell you how to encode some message. My message is A, it consists of like 9 symbols. And I'm gonna write the code word here. So the first thing I'm gonna do is just like copy the symbols of the message. Now I'm describing a non-online encoding function, but it will be easy to see why this thing is online. So for now, I'm just telling you how to encode this one shot. So you write down the message. That's simple. And then I'm going to have a logarithmic number of threads. So log 9 is 3, maybe, approximately. And so I'm going to have so 4 threads, 3 plus 1. And in every thread, I will be encoding chunks of the message using C. Okay? How exactly? So in the first thread, I will be encoding chunks of size 1. Very simple. So at time step 2, after I finished reading the first symbol, I will spit out the encoding of the first symbol. I will spit out an encoding of a chunk a time step after I finished reading it. So at time step 3, I will spit out the encoding of the chunk A2, so on and so forth. Okay. This square is more than a message symbol because I'm working with Reed Solomon, but it will be.
How do you encode it? So you first encode the bits. What's the encoding?
Embed it into some finite field, like the finite field from here.
Okay, but usually when you think of Reed Solomon, you encode n symbols. You don't encode one symbol. Like, but you're saying, okay, I'm going to encode one.
N equal 1. Yeah.
Okay, so you encode. Okay, so A is like then. Sorry. Okay, so A0 tilde you encode A1, you encode A2, you encode A3, and so on. And then what do you do next? You encode A1 and A2 together? No,
yes, that's the next step. But for now, in this thread, I'm just encoding individual symbols as if they were messages.
But what happened to the A1? Why did you put an empty box? I feel like
Here, because I encode AI at time step I plus 1.
Okay.
I wait till I finish reading like the symbol, because the point is that with block codes are not online, so you can encode the message only after you finish reading.
Got it.
I mean, potentially I could encode it already here, but this is simpler.
Okay.
So you're saying the string of the code word is like row-wise?
Right, but this will come later. Now to the more like non-trivial part of the construction, when we're encoding two symbols. I will encode the message consisting of A1 and A2 together after one time step after I finished reading A1 and A2. So that would be time step 3. So at time step 3, I will kind of write down the encoding of A1 and A2 together. Okay, A3 and A4 will come at step 5.
The A3 now is already the encoding of the original A3?
No, it's A3 actually.
It's A3. Okay.
You guessed it right. In the next thread, I will be encoding messages of length 4. In thread I will be encoding messages of length 2 to the I.
And it's always contiguous substring?
Say again?
It's always like contiguous messages of length 4, like it's a substring of length 4, and it's not like all possible.
Yeah, it's the chunk in the message that is these 4. Yeah, exactly. It's chunks, yeah.
And these threads are running in parallel.
Yes.
You run all of them.
Yes, logarithmic number of them. Good. So, I mean, this doesn't look like a code word, just like a bunch of code words. My code word, like the ith symbol of my code word, will be pictorially like just this row. More formally, maybe, like let's say that the rate here is half, so like encoding of a message of length 2 is like 4 symbols, so you'll just like add 2 symbols here and 2 symbols there, okay?
So you're using a Solomon code with the fixed, the constant rate,
yes,
regardless of block size.
Yes, and I can work with extension fields that, with the tower of extension fields as I have more and more threads.
Yeah, to combine.
Yeah.
Sorry, why is it online? Why can you do it like online? Because when you add something to a code word, it changes the entire code word, of course, right?
Yeah. So no, but so like let's say I'm I don't know, like, so notice that every block code word that you're writing, you already know the message entirely. Why? Because to like write this one, I waited till I get the entire message.
Okay. You're allowed to depend on all the. Okay.
Yeah. You're allowed to depend on everything.
And the past in your path.
Yeah.
Okay.
Now this doesn't look like what I promised you, that the prover looks at only few locations when he encodes, but this is, we're tensoring this, and this is not the code we're actually using, just like the atomic structure. And annoyingly, sometimes you will not have like entire code words. Sometimes you'll just have parts of code words. Annoyingly for the analysis, not for anything else. Yes.
So you're saying that you're starting, you're moving things down so that you know the entire thing.
Exactly. Otherwise, you couldn't.
But you're also assuming that then you can, even if this is very long block, you can encode it instantaneously. Wouldn't you need also some extra time?
Yes.
Yeah.
If talking about this code, it will take you a lot of time, but we like kind of amortize things and we play with it.
Like you can start computing the encoding before you know the entire code.
And also like I will be encoding short parts of the eventual message using this. It will, speaking ahead, we'll use a tensor code where every row is this, so I will be actually working with small stuff.
Or you could also move it by 2 positions instead of 1, so that
when you start writing them down. Why 3 distance hold? Because so starting the first disagreement, let's say the first non-zero appeared at A3, but after that I still have 0, so my only non-zero is here. So you can see that every like row here is kind of affected by the error. And I use like the error correction to spread out the error. So I know that, like, for example, between time 5 and 8, I have like a certain amount of errors here, which cover me for this period of time. Good.
This is to be one over log, right?
Yeah.
The rate.
Rate.
The rate. Yes. Yes. I don't care. Tree code people care because it's interesting. That's why they've been like researching this since the 90s. But we're anyway gonna pay like polylog factor, so this is like the least of our problems. And I really recommend like reading some tree code stuff. They're really interesting. Not this one. This one is nice, but there are some very beautiful constructions. Okay.
Don't like take this big row symbol and kind of error correct it or
kind of what?
Do error correction per row. You're saying you send
no just yeah just this. For me, like a row is an entire symbol, so even if like just one bit is non-zero, for me it's a non-zero symbol. Good. Great. So we've seen a tree code. Let me show you how locally testable tree codes look like, because we do need them for 3 PCPs. But first, let me define what locally testable codes are. So these are codes where you have a test algorithm that can be random. And if you give this test a code word, it will accept. If you give this test a non-code word, it will reject. Now, in what probability? It depends on your notion. The strongest you can hope for is that you always reject a non-code word with non-zero probability. Like even if your oracle differs by just few bits from a code word, then you have some chance of catching it, and this chance grows with the distance of the oracle from the code. And usually this alpha is like good enough. Okay.
Is this something you're defining?
No, locally testable codes have been defined. We generalize this for locally testable tree codes.
That's you're defining.
Yes. Yeah. The only difference is that I mean a locally test a tree code is in particular a code.
Yeah, of course.
But just like for infinite, like it's an infinite code. The only difference is which distance metric you care about, and here we care about tree distance, not Hamming distance. And the thing is that T reads just few symbols, otherwise you could have read everything and like get a perfect test. Right? Okay. How do you get local testability? Usually, without even out of the context of tree codes. So a very popular method is tensoring. It's called tensoring. So what is tensoring? You start with a linear code over some field. And let's say, so I will show you first for how it works for block codes. So in block codes, you have a fixed length, right? And the tensor of this code, let's say of dimension 2, like it's the set of all matrices where every row and every column are a code word in the original code. Very simple. And it's easy to see, and it's known that like the rate and the distance don't decrease by a lot. You can extend it to like more than one dimension, and you get like a proportional loss in rate and distance. But why is tensoring good? Because if it gives us local testability, and the local test is actually very simple. It says like sample, like let's focus on the 3-dimensional case. It says like sample a uniformly random plane in a uniformly random parallel to a uniformly random axis, and just test that this plane is what you'd expect, which is a code word in the 2-dimensional tensor. Like you check that every row and every column there is a code word in the original code. Okay, and it has been shown that this works generally. Like if you take any code, you tensor it 3 times, you will get a locally testable code. And if you want to go more dimensions, you get even a better complexity. Good. So what happens when we try to apply this to tree codes? So like tensor tree codes are well defined. As long as your tree code is linear, you can tensor it, and then you can look at the tensor. What happens here? So it's no longer the case that the test works, because let's imagine that we have like the first error appears only at the end, so in this corner. If I would sample a plane uniformly, I would catch this error with very low probability. The tree distance here is 1, but I will catch it only with probability 1 over n, which is super bad. So I do a very simple thing. I just like look more towards the end, right? So I'm not going to sample a plane with probability 1 over n. I'm going to sample it with probability 1 over I. Like this miraculously works well. So that's the harmonic distribution. The last plane you sample with probability 1, the next probability half, third. This is not a probability, this is a function, so you normalize, right? And you get some loss, but it's fine. So it's like a skewed plane tester. And we show in a previous work that this actually works for tree distance. With this distribution, you can actually catch tree distance. Okay? However, unfortunately, like tensoring tree codes doesn't give you a tree code. Tensoring a block code will give you a block code because you're anyway working with a fixed length. You say, okay, you get a message, you put it in a matrix, and you encode it, whatever. Tree codes need to work with messages of any length. So we cannot always hope that we have like this beautiful cube, right? At one point, if we have this, we're going to add a new symbol, and then where do we put it? It's not clear. So we deal with it also in this previous work. We devised a way like to add symbols in this 3D space. So we're kind of embedding the one-dimensional timeline into this high-dimensional space, and for this we like follow a very particular walk that works for us, and the analysis works and everything.
So the previous work was just building tree codes that are locally testable. It has nothing to do with PCP. Then you have a follower that does it for users that get PCPs.
And the nice thing, like, there are many walks that you can imagine over this, over the high-dimensional space that are monotone, are fine, and give you a good syntax. But what we use, what is like special about this walk is that at any point in time, you can cover this weird object using a constant number of very beautiful objects, right? Rectangles. And each of these you can test.
It's a very nice picture.
Thank you.
But, congratulations. But I don't understand what's the definition of this partial tensor. Can you define?
Yes. So, okay. So with block codes, I'm describing the problem in a very high level. If you would want to get a locally testable block code, you could start with a block code and say I'm going to tensor it, and tensoring it will give you the syntax of a block code. Why? Because you have a message of length 99, you make it 100, and then you write it down as a 10 by 10 matrix and you encode it.
So partial tensor is a requirement in some sense.
It's not. It's like an artifact of requiring this online encoding because you have to deal with a message with any length.
No, but I'm asking what's the definition? You're saying the definition is what you want. It's like at the end what you want to be able to get out of it.
So at the end, I want to actually a tree code with an online encoding function. And tensoring doesn't give me an online encoding function. It gives me some sort of online encoding in like many dimensions.
Okay, and a partial tensor.
And what we do is we take, to move from high-dimensional timeline to one-dimensional timeline, we pass through like partial objects. Because essentially you want to tell me like where do I put the symbol at time 17, and where do I put the next symbol and the next symbol and so on. And this will be defined by some embedding from the natural like the one-dimensional coordinates to the three-dimensional coordinates. And along the way you will have these partial tensors. But eventually you will take this and write it down as a string. But I do like this tensor structure is underlying our analysis all the time because we need it for local test. Okay?
So the partial tensors are tensors between predicts?
No, partial tensors are really like think about having three messages that agree in some prefix in their intersection, and I'm encoding each separately. When you're going to merge them, you're going to have something consistent because your encoding is online, so where they intersect, they're consistent. And this partial thing is just like the merge of them. It's well defined because where they intersect, they are consistent. Okay? The nice thing, okay, maybe I wasn't clear, but when you're tensoring 3 codes, you can actually like add a symbol here, as long as you have like the high dimensional prefix of it. Like as long as if you look back on all dimensions, if you already have the information there, then you can continue encoding. That's the thing. Yes?
In what sense is this monotone? Like what is the word monotone referring to?
So, okay, so usually, so what I want is whenever I'm adding a new symbol, I've already covered its high dimensional prefix, and by that I mean all coordinates that are less or equal than the next coordinate in all of the dimensions. Whoever knows like tensor codes, the way you encode tensor codes is row by row and column by column. And if I have this monotonicity, this allows me to encode row by row and column by column, because in 3 code I have to have the past information.
Yeah.
Any more questions? Okay. So I don't have much time left, but let me tell you about some of the challenges beyond like building locally testable 3 codes, because there are still many. Okay, we had this paradigm in mind. We said, okay, let's represent our statement as a string that is all zeros only if the statement is correct, and let's put it in the PCP. But this is clearly not sound, because the prover can always like print out zeros. That's not the problem, right? You need to somehow connect this string with your statement, with your actual statement. So what's actually done is that your PCP is actually an encoding of the witness. And the way you get this all zero string from a witness, you somehow simulate in the like code word space. Similar to FHE, but like for codes, not for encryption. So you want to kind of homomorphically evaluate the code word that encodes this given the encoding of the witness. And then
Isn't it more like BFLS as opposed to like...
This is BFLS, yeah. I should have added the... Good. So okay. So let's recap. So the verifier first tests that this is a code word, and he wants to test that this is all zeros. But how does he get this? The PCP doesn't contain this. It only contains the witness. So we need somehow to be able to evaluate any symbol here by looking at only few symbols here. That's how usually PCPs work. And maybe to give more sense, in PCP for NP, this is, roughly speaking, corresponds to the evaluation of the 3 CNF clauses of your 3-set instance. And then really each of these symbols can be computed locally by just looking at 3 locations. And really, if your circuit is satisfiable, then this should be all zeros, as in all of the clauses are satisfied. And because these are all local functions, there is some hope to compute them locally also in the code word space. Good. Just want to say that I'm oversimplifying here. We don't really actually just like look at random locations and hope to catch a non-zero. We need a more sophisticated protocol, because it's not the case that this is all zeros in incompleteness. It holds that some prefix is 0, so we need to be more careful. But we do build like a sum check protocol that is in par with this like incremental syntax. It's important also. So okay, I don't have much time left, but I want to say that the main challenge is in this part. And why is that? So okay, so like standard PCPs, how do they do this? It turns out like we have block codes that are very nice. They are very algebraic. For example, Reed-Solomon, just a polynomial, right? And let's say we want to like evaluate addition. So addition is fine. You can do with any linear code. You add two symbols from 2 different code words, you will get the symbol in their in the encoding of their addition. It turns out that with Reed-Solomon you can do this also for multiplication. They're very and not only addition and multiplication. You can do lots of shifts, operations that are more combinatorial in nature, and so on. 3 codes are like, they look like this. Like, come on. And we don't really know like purely algebraic tree codes. All of the tree codes that we know that have reasonable alphabet size, at some point they involve some combinatorial tricks. So here, like, okay, we are using these blocks that can be very algebraic, but then we're just like attaching them to each other. And the challenge in this work was really like translating the capabilities that algebraic block codes give us to Schulman's construction.
Do you actually use the specific construction that you gave of Tamer, or do you can take any tree code that's locally testable and upgrade it to a tree PCP?
So to get local testability, you can use any error correction code. For this to work, I need just that the base code satisfies these nice properties. I don't care if it's Solomon, it can be anything, but as long as it satisfies like this, it allows you to evaluate constraints under the hood. As long as this holds, I am positive that applying this structure using our techniques will still allow it.
We sort of rely on two levels. It's both the Schulman construction and the instantiation via Reed-Solomon.
Yeah.
Yeah, but I'm asking the instantiation of Reed-Solomon. I understand that you need it for local testability. What else?
No, not for local testability.
For local testability, take any tree code and tensor it.
I see. So sorry. So what are you using the Reed-Solomon for?
For the multiplicative relation, kind of. So Reed-Solomon has the property when you multiply code words instead of code words.
I see.
And we need to inherit it.
I see.
And because we're going through the combinatorial step of this thing, it's messier.
I see. Got it. Okay, thanks.
Yeah. Yes. Okay, so yeah, I mean, I guess you're all hungry and there's lunch now, and I'm out of time, right? So yeah, so that's the like challenge in a very high level. To deal with it, you really need to like do some work. Hopefully, you're motivated to read the paper now. Say again.
So with this analogy of history, wherever things decay, so there are errors that happen over time. Nothing changes, I guess.
I guess like you can.
Bound.
So you mean in the proof?
Yeah.
So you can model this as like this. This is even weaker than adversarial error. So as long as like not too many errors happened, I think. I mean, we don't have. You need to still like to prove the theorem, but I'm positive that it should still hold.
Yeah.
Like,
Are you asking for
it should still be fine.
tolerant that it will still accept, even if the proof?
I'm positive it still should be fine because all of this is based on like checking that things are close to code words and so on and so forth.
And I'm looking at random places, so you would know.
So you either can tell if not too many errors happen, you can either tell that. Some errors happened if there are like mildly many errors, or accept like know that the statement is true. Have sounds. Let me just like go to the open question section. Of course, going beyond the bounded space computation, most generally you would like to give your circuit arbitrary random access to the history. That's what happened on the blockchain, right? For example. Everything I'm saying here, I think, would require new techniques. Reduce query complexity, of course, that's obvious. And maybe more straightforward constructions, like all of the amazing work that has been done to PCPs, maybe we can start to apply it to 3 PCPs if they're interesting enough, I'm not sure. But if they are, then like more straightforward constructions might lead to more efficient constructions. But this, I feel that this will require like better or like more straightforward algebraic tree codes. And some very serious people have been trying to do that for decades, but I have trust in you. So. 3 IOPs, I think that's what we were hinting at. DAG PCPs. This would be the analogy to proof carrying data. Okay, there are many things to explore. That would be it. Thank you.
Hey, any other questions?
Maybe can you summarize like high level? I'm just trying to wrap it. It's totally beautiful. So it seems like this is much better than like doing this, smart. But like conceptually, how do you use PCPs globally? Is it just like a technical tool to overcome this switching between random walk over this? So it's an object of independent interest.
I think it's in particular independent. Like it's interesting by itself. Maybe not like. I think if you want to talk about like comparing it in like in applications, I think if you don't care about large memory anyway, this is your way to go. The main drawback here, at least asymptotically speaking, is that you need to like maintain the state.
Let me just understand and make sure I understand. So it's like the classic IBC is like the generation, when you verify, you just lose all access to what happened before.
Yes.
You just have the short proof. This you don't get.
Right.
Right. Okay.
Maybe with some memory checking tricks with CRA, maybe you can, I'm not sure. Yeah, and also I think this I'm not sure what's the, I'm not sure what's happening in IBCs, but I think this has the potential to allow more general computation. Like I'm aware that you can, in IBCs you can always like generalize using like tricks on tops, but this kind of, there's the hope that this can give you natively like IBC for computation with large memory. Yeah, but this is like very big. So what I'd say, there's like, I think in my opinion, there's potential. Also to be integrated with IBCs and so on. Yes?
The IBCs that this implies in the ROM, is that provably secure in the ROM?
Yeah. It's just Killian, nothing too fancy. It's just we use the fact that Merkle hash trees are incremental.
Okay, so thank you so much.